Hello all, welcome back to Aislyn Technologies YouTube channel. Today we're going to see about lung tumor detection using machine learning. First, I'll explain you the abstract here. Our abstract explores the use of computer-aided diagnosis (CAD) tool to enhance tumor characterization from radiological image, aiming for improved accuracy and speed. It highlights the importance of non-invention cancer staging, prognosis, and personalized treatment planning. The author proposes supervised and unsupervised machine learning strategy, including a proportion SMV approach inspired by learning from the label proportion LLP mentioned in computer vision. The study evaluates these algorithms on lung and pancreatic tumor diagnosis using a dataset of 1018 CT scans and 171 MIR scans, achieving a state-of-art sensitivity and specificity results. Now I'll explain you the introduction. In the introduction, the pancreas is highly lethal, with most patients diagnosed at the advanced stage, resulting in poor survival rates. The median survival is limited to 6 months for metastatic cases and 10 months for local advanced disease. The CAD systems are developed to aid radiologists in making rapid and accurate diagnostic decisions by minimizing false positives and negatives, with a particular focus on increasing sensitivity. The computerized analysis of imaging features is crucial for enhancing diagnostic accuracy across various types of tumors, including those in breast, brain, lung, liver, and prostate. Now I'll explain our problem statement. In a problem statement, there are three challenges. For one is dataset challenge. The preparation of suitable dataset is a significant challenge for machine learning algorithm. This study uses LIDC IDRA dataset, which is one of the largest publicly available nodal datasets, annotated by up to four radiologists for nodals 3.0 mm or larger. Interclass variation challenge. A major challenge in detecting tumor, particularly in the pancreas, is the large interclass variation because by the diverse shape of pancreatic tumors. Complexity in detection. Tumor detection is complicated due to the variability in tumor area and difficult in accurately determining the tumor's position, shape, size, and texture. I will explain objective. Our primary objective is to develop an automated method using AI for detecting abnormalities in lung images. Given the lung cancer is not preventable, early detection is crucial for improving survival rates. The aim is to provide precise information about the affected areas to facilitate appropriate treatment, ultimately protecting patients from lung cancer. Yeah, this is our advantage. Automatic tumor detection is helpful to doctor as well as patient. The manual identification is not fast, accurate and efficient. To overcome the problem is application is design. This application is design. Now I'll show you a training code. Yeah, here's a training code. First, I'll explain this function. The morphological function is applies an additive threshold and a morphological operation for erosion and dilation purpose, for what means to enhance the features in image in a particular area, for separating a small objects like potential tumor from the background. And then it uses the connected components to identify and filter out some small pixels based on minimum value. And then here we are reading and labeling, here reading and label files. This is used to a text file containing a file names corresponding labels, whether it's true or false. It connected components to identify and filter out some pixels values based on and labels are converted into zeros. And labels are converted into zeros for true and false, and the presence of tumor is 1 and false is 2. Here, we are reading all the images and processing it. First, we will read the pixels and then we are applying contrast limited adaptive histogram equalization for contrast enhancement and calling the morphological operation to segment the images. And here we are merging our and resizing the images into 120 to 120 pixels and normalizing pixels value between 0 to 1. Here we are loading our training data set, and this is our data set path. Now this is a CNM model definition. Here we use three conventional with relo activation and max pooling layer to reduce its dimensionality. And the flatten layers is converted to 2D from 1D array. There's a two dense layers for classification. The layer 36 output is an appreciable for different class of tumors. So that we are given 36 here, and then we will, after the building model, we place our test training part here. By we will evaluate model using this test loss and test accuracy. After this work, the trained model CNN.h5 will be saved outside, and the model is trained about 10 epochs for the training data, and validation data is provided, and we can monitor validation by this. And in and in our, after our model is saved, in our curve is to plot the axis the model performance across the different threshold, so that we give our curve here. So after our training, our model will be saved outside. Yeah, after our training, our model will be saved outside like this, trained model CNN. Now I will show you our testing code. Yeah, here is our testing code. First, we will import all the modules, and then here we import our morphological operation. Here we use the same adaptive threshold, erosion and connected, and we use dilation also. And then in here we are listing our what kind of here we listed, and then list we are give two strings. One is detected lung cancer, another is normal cancer. After this, in this part, the code prints the metadata such as mortality, type of scan, manufacturer, and here it will print the age of patient, sex, name, and their ID. After this, image processing will be done here. Nothing but our pixel. After this, the pixel data from DICOM file is extracted, and a histogram. Here our in histogram equalization, our contrast enhancement of image is performed using contrast limited adaptive. So we're doing here, and then we have segmentation purpose to perform an image segmentation, and finally we will merge our image. Uh, Here the merge the original equalized and segmented image into one. Finally, we will do resizing here into 128 into 128 pixels. And finally, your model will be saved here. Based on this model, you will do prediction. Now I'll run this so that you have a good look on this. I'll show you the output. Now I want to select any one of these. So you can see this. This was the original image. This histogram equalized image, and this merge of histogram and input image. This is a processed image. You can see the predicted is normal lungs, and then the age of and the patient age is female, And her another age is 71. This is the patient ID. I'll do for other input now. You can see. Yeah, this is the input. This is the histogram equal as image. Weighted merge of histogram and input image. This is processed image. Yeah, this to a normal image. The patient age is 68. Gender is male. Patient ID and its name are predicted as normal lungs. I hope you have a clear idea of this project. If you have any doubt, you can pin a comment in comment section and don't forget to like, share and subscribe. Thank you.